In elementary geometry, a polytope is a geometric object with flat sides, and may exist in any general number of dimensions n as an n-dimensional polytope or n-polytope. For example, a two-dimensional polygon is a two-polytope and a three-dimensional polyhedron is a three-polytope. Some theories further generalize the idea to include such objects as unbounded, decompositions or tilings of curved manifolds such as spherical polyhedra, and set-theoretic abstract polytopes. Polytopes in more than 3 dimensions were first discovered by Ludwig's currency Flee. The term polytope was coined by the mathematician Reinhold Hoppe, writing in German, and was introduced to English mathematicians in its present form by Alicia Boole-Stott. Approaches to definition. The term polytope is nowadays a broad term that covers a wide class of objects, and different definitions are attested in mathematical literature. Many of these definitions are not equivalent, resulting in different sets of objects being called polytopes. They represent different approaches to generalizing the convex polytopes to include other objects with similar properties. The original approach broadly followed by Ludwig's currency Flee, Thorold Gossett and others begins with the extension by analogy into 4 or more dimensions, of the idea of a polygon and polyhedron respectively in 2 and 3 dimensions. Attempts to generalize the Euler characteristic of polyhedra to higher dimensional polytopes led to the development of topology and the treatment of a decomposition or CW complex as analogous to a polytope. In this approach, a polytope may be regarded as a tessellation or decomposition of some given manifold. An example of this approach defines a polytope as a set of points that admits a simplicial decomposition. In this definition, a polytope is the union of finitely many simplices, with the additional property that, for any 2 simplices that have a non-empty intersection, their intersection is a vertex, edge, or higher dimensional face of the 2. However, this definition does not allow star polytopes with interior structures, and so is restricted to certain areas of mathematics. The discovery of star polyhedra and other unusual constructions led to the idea of a polyhedron as a bounding surface, ignoring its interior. In this light, convex polytopes in p-space are equivalent to tilings of the sphere, while others may be tilings of other elliptic, flat or toroidal surfaces. C elliptic tiling and toroidal polyhedron. A polyhedron is understood as a surface whose faces are polygons. A 4-polytope is a hypersurface whose facets are polyhedra, and so forth. The idea of constructing a higher polytope from those of lower dimension is also sometimes extended downwards in dimension, with n seen as a 1-polytope bounded by a point pair, and a point or vertex as a 0-polytope. This approach is used for example in the theory of abstract polytopes. In certain fields of mathematics, the terms polytope and polyhedron are used in a different sense. A polyhedron is the generic object in any dimension and polytope means a bounded polyhedron. This terminology is typically confined to polytopes and polyhedra that are convex. With this terminology, a convex polyhedron is the intersection of a finite number of half-spaces and is defined by its sides, while a convex polytope is the convex hull of a finite number of points and is defined by its vertices. Elements. A polytope comprises elements of different dimensionality such as vertices, edges, faces, cells and so on. Terminology for these is not fully consistent across different authors. For example, some authors use face to refer to a dimensional element while others use face to denote a two-face specifically. Authors may use J-face or J-facet to indicate an element of J dimensions. Some use edge to refer to a ridge, while HSM Coxeter uses cell to denote an dimensional element. The terms adopted in this article are given in the table below. An n-dimensional polytope is bounded by a number of dimensional facets. These facets are themselves polytopes, whose facets are dimensional ridges of the original polytope. Every ridge arises as the intersection of 2 facets. Ridges are once again polytopes whose facets give rise to dimensional boundaries of the original polytope, and so on. These bounding subpolytopes may be referred to as faces, or specifically J-dimensional faces or J-faces. A zero-dimensional face is called a vertex, and consists of a single point. A one-dimensional face is called an edge, and consists of a line segment. A two-dimensional face consists of a polygon, and a three-dimensional face, sometimes called a cell, consists of a polyhedron. Important classes of polytope equals convex polytopes equals. A polytope may be convex. The convex polytopes are the simplest kind of polytopes, and form the basis for several different generalizations of the concept of polytopes. A convex polytope is sometimes defined as the intersection of a set of half-spaces. This definition allows a polytope to be neither bounded nor finite. Polytopes are defined in this way, for example, in linear programming. A polytope is bounded if there is a ball of finite radius that contains it. A polytope is said to be pointed if it contains at least one vertex. Every bounded non-empty polytope is pointed. An example of a non-pointed polytope is the set. A polytope is finite if it is defined in terms of a finite number of objects, for example, as an intersection of a finite number of half-planes. Regular polytopes equals. A regular polytope is the most highly symmetrical kind, with the various groups of elements being transitive on the symmetries of the polytope, such that the polytope is said to be transitive on its flags. Thus, the dual of a regular polytope is also regular. There are three main classes of regular polytope which occur in any number n of dimensions: simplices, including the equilateral triangle and the regular tetrahedron; hypercubes or measure polytopes, including the square and the cube; orthoplexes or cross polytopes, including the square and regular octahedron. Dimensions 2, 3 and 4 include regular figures which have fivefold symmetries and some of which are non-convex stars, and in 2 dimensions there are infinitely many regular polygons of n-fold symmetry, both convex and star. But in higher dimensions there are no other regular polytopes. In 3 dimensions the convex Platonic solids include the fivefold symmetric dodecahedron and icosahedron, and there are also 4-star Kepler-Poinsot polyhedra with fivefold symmetry, bringing the total to 9 regular polyhedra. In 4 dimensions the regular 4 polytopes include 1 additional convex solid with 4-fold symmetry and 2 with 5-fold symmetry. There are 10 star-Solar currency Flea-Hesse 4 polytopes, all with 5-fold symmetry, giving in all 16 regular 4 polytopes. Star polytopes equals. A non-convex polytope may be self-intersecting. This class of polytopes include the star polytopes. Some regular polytopes are stars. Generalizations of a polytope infinite polytopes equals. Not all manifolds are finite. Where a polytope is understood as a tiling or decomposition of a manifold, this idea may be extended to infinite manifolds. Plane tilings, space-filling and hyperbolic tilings are in this sense polytopes, and are sometimes called airatopes because they have infinitely many cells. Among these, there are regular forms including the regular skew polyhedra and the infinite series of tilings represented by the regular airogon, square tiling, cubic honeycomb, and so on. Abstract polytopes equals. The theory of abstract polytopes attempts to detach polytopes from the space containing them, considering their purely combinatorial properties. This allows the definition of the term to be extended to include objects for which it is difficult to define an intuitive underlying space, such as the 11-cell. An abstract polytope is a partially ordered set of elements or members, which obeys certain rules. It is a purely algebraic structure, and the theory was developed in order to avoid some of the issues which make it difficult to reconcile the various geometric classes within a consistent mathematical framework. A geometric polytope is said to be a realization in some real space of the associated abstract polytope. Complex polytopes equals. Structures analogous to polytopes exist in complex Hilbert spaces where n real dimensions are accompanied by n imaginary ones. Regular complex polytopes are more appropriately treated as configurations. Duality: every n-polytope has a dual structure, obtained by interchanging its vertices for facets, edges for ridges, and so on, generally interchanging its dimensional elements for dimensional elements, while retaining the connectivity or incidence between elements. For an abstract polytope, This simply reverses the ordering of the set. This reversal is seen in the Solow-Currency-Flies symbols for regular polytopes, where the symbol for the dual polytope is simply the reverse of the original. For example 4, 3, 3 is dual to 3, 3, 4. In the case of a geometric polytope, some geometric rule for dualizing is necessary, see for example the rules described for dual polyhedra. Depending on circumstance, the dual figure may or may not be another geometric polytope. If the dual is reversed, then the original polytope is recovered. Thus, polytopes exist in dual pairs. Self-dual polytopes equals. If a polytope has the same number of vertices as facets, of edges as ridges, and so forth, and the same connectivities, then the dual figure will be similar to the original and the polytope is self-dual. Some common self-dual polytopes include, every regular n-simplex, in any number of dimensions, with Schläfli symbol 3n. These include the equilateral triangle 3 and regular tetrahedron 3, 3. In 2 dimensions, all regular polygons; in 3 dimensions, the canonical polygonal pyramids and elongated pyramids, also the infinite square tiling 4, 4. In 4 dimensions, the 24-cell, with Schläfli symbol 3, 4, 3. History. Polygons and polyhedra have been known since ancient times. An early hint of higher dimensions came in 1827 when Paragraph Bias discovered that 2 mirror image solids can be superimposed by rotating one of them through a 4th mathematical dimension. By the 1850s, a handful of other mathematicians such as Cayley and Grassmann had also considered higher dimensions. Ludwig Solow-Currency-Flies was the first to consider analogues of polygons and polyhedra in these higher spaces. He described the 6 convex regular 4 polytopes in 1852, but his work was not published until 1901, 6 years after his death. By 1854, Bernhard Riemann's Habilitationsschrift had firmly established the geometry of higher dimensions, and thus the concept of n-dimensional polytopes was made acceptable. Solow-Currency-Flies polytopes were rediscovered many times in the following decades, even during his lifetime. In 1882 Reinhold Hoppe, writing in German, coined the word polytope to refer to this more general concept of polygons and polyhedra. In due course Alicia Boole-Stott, daughter of logician George Boole, introduced the anglicized polytope into the English language. In 1895, Thorold Gosset not only rediscovered Solow-Currency-Flies regular polytopes but also investigated the ideas of semi-regular polytopes and space-filling tessellations in higher dimensions. Polytopes also began to be studied in non-Euclidean spaces such as hyperbolic space. An important milestone was reached in 1948 with H.S.M. Coxeter's book Regular Polytopes, summarizing work to date and adding new findings of his own. Meanwhile, the French mathematician Henri Poincaré copyright had developed the topological idea of a polytope as the piecewise decomposition of a manifold. Branko Gra 1/4 nBaum published his influential work on convex polytopes in 1967. In 1952 Shepard generalized the idea as complex polytopes in complex space, where each real dimension has an imaginary one associated with it. Coxeter developed the theory further. The conceptual issues raised by complex polytopes, non-convexity, duality and other phenomena led Gra 1/4 nBaum and others to the more general study of abstract combinatorial properties relating vertices, edges, faces and so on. A related idea was that of incidence complexes, which studied the incidence or connection of the various elements with one another. These developments led eventually to the theory of abstract polytopes as partially ordered sets, or posets, of such elements. McMullen and Schult published their book Abstract Regular Polytopes in 2002. Enumerating the uniform polytopes, convex and non-convex, in 4 or more dimensions remains an outstanding problem. In modern times, polytopes and related concepts have found many important applications in fields as diverse as computer graphics, optimization, search engines, cosmology, quantum mechanics and numerous other fields. In 1913 the amplituhedron was discovered as a simplifying construct in certain calculations of theoretical physics. Applications. In the study of optimization, linear programming studies the maxima and minima of linear functions constricted to the boundary of an n-dimensional polytope. In linear programming, polytopes occur in the use of generalized barycentric coordinates and slack variables. In twistor theory, a branch of theoretical physics, a polytope called the amplituhedron is used to calculate the scattering amplitudes of subatomic particles when they collide. The construct is purely theoretical with no known physical manifestation, but is said to greatly simplify certain calculations. See also. References, Notes. Sources. External links, Weierstein, Eric W., Polytope, Math World. Math Will Rock Your World. A Euro application of polytopes to a database of articles used to support custom newsfeeds via the Internet. A Euro, regular and semi-regular convex polytopes. A short historical overview.